Welcome everyone for the afternoon session of our place. And this is where we'll something from Beijing. We will tell about one ways of skein from unpunctured surfaces.
Introduction, and thank you very much for the invitation. So let me begin with the overview. Well, I think in this conference we haven't really defined what is a class algebra. I will not define them. So to be sure, a class algebra in my mind is an algebra that has a lot of charts. It's like you have a manifold has a lot of charts, and class algebra is nothing different. And so this is a very elementary concept, just like a manifold. So many algebras, they have natural charts, so they are class algebras. In particular, we are most interested in two kinds of class algebras. One are those arising from coordinate rings of some important varieties from Lie theory, like Lie groups, for example. And another, these are the class algebras. These are class algebras are actually skein algebras of surfaces, like in knot theory. Unfortunately, here we are not yet talking about skein modules. So for class algebra, at least in the theory of class algebra, usually we are talking about skein algebras. So if you look at Lie theory and you look at a complex coordinate ring of a variety A, here K is the base ring you are looking at, for example, complex field or the complex version. And you might be talking about combinatorics and resembling theory of this Lie theory, or you might be talking about Kazhdan-Lusztig type basis of in this Lie theory. For example, you have the Kazhdan-Lusztig type basis for H algebras for quantum groups, right? That is the quantum basis. And in skein algebra, there are different structures that you are looking at. You might be looking at topological invariants, and in particular, you might be talking about topological quantum field theory that you are using cobordism to construct some monoidal categories, and you can construct those of them. You see that in different areas where we have very different structures, but now they are unified under the common framework of class algebras. So it's natural to ask, can we compare and understand different structures in a common framework of class algebra? So this is the basic idea. And I'm not saying that there are not other important families, but as far as I'm concerned, I think the families of class algebra from Lie theory and those from surfaces, these are for the moment, these are the most well understood families that were. What is A? A is any variety that you might be interested in from Lie theory, like Lie group, for example, or like in this talk in Oya's talk, you have a product of many flags, and that is also something kind of. Well, we have many coordinate rings from Lie theory. Like in Professor King's talk, we have homogeneous coordinate ring of Grassmannians, and many of them they are class algebras. And also there are those things which are not class algebra. For example, if you take the full flag variety, as far as I know, they are not class algebra. Okay, so now let us look at what kind of common structure can we talk about in class algebra? So there's a basic problem in class algebra, namely to study their basis. Well, the algebra at first is a vector space, so we have basis. So about 24 years ago, Hermann and Lusztig, they invented class algebra, which is known as A, to study why is the total positivity in the sense of Lusztig. Namely, we study the matrices with non-negative minors, and we use the Lie theory to understand these matrices. And we will also have the important dual canonical basis of quantum groups in the work of Kazhdan and Lusztig. For representation theory, first we arrive at the canonical basis, and also for geometry representation theory, we have the canonical basis. But here you have a natural non-degenerate pairing of this quantum group, so we take the dual basis, and that is the correct setting. We'll consider the basis for complex coordinate rings. And then they have the following ambitious expectations. Namely, for many varieties from Lie theory, they hope that the coordinate ring is a class algebra. And moreover, because the quantum group might take this form, they hope that using this language of class algebra, we can actually generalize the version, the construction of dual canonical basis. Say we might have an analog of dual canonical basis for many coordinate rings. And moreover, this construction should be compatible with the class structure itself. It should contain all the class monomials. We will see that soon. So these are some combinatorial objects which are recursively defined using some algorithm inside this class. In fact, one of their motivation is that the canonical bases themselves, they are quite difficult. They are essentially curved shapes. And they hope that using this combinatorial object for class algebra, they might have an algorithm to kill these elements. Okay, and now by series of my work, I introduced something called common triangular basis. Common means that it is common for every chart. So basically, it's a global definition. Triangle means that it has some triangularity, just the triangularity between canonical basis and p-diagonal basis. We have certain basis, common triangle basis L, and I claim that it is an analog of this different basis. So from this point of view, from this B theory, it works very well. Okay, and why we are interested in basis? So knowing basis is very important because in general, this quantum class algebra, they are infinite dimensional vector space. If you know the basis, you have some basic control of this infinite dimensional vector space. For example, there is a class algebra, there is also the quantum class algebra by some contradiction. And they can be naturally defined, but in fact, we don't know if the quantum version has the classical limit, give you the classical version. So, but if you know their basis, then you can easily show that taking the classical limit, the quantum version goes to the classical version. So this is what we really need for deformation condensation to make sense. Otherwise, you define something classical, define something quantum, but they are not related, so it's not so convenient. And also we can have the specialization, namely, in quantum class algebra, we can naturally define this over this Laurent polynomial ring over Q, where Q is a formal parameter. So this is in Lie theory, we call this an integral form. So in class theory, we get integral form by Swift, because the definition is not sensible about space. And once you know the other basis, then you can do the base change. You can change the definition domain of this quantum class algebra over any commutative ring. And this Q can be replaced by any invertible element in this commutative ring. So for example, you can work with the characteristic key, and you can work with the roots of unity. So this makes sense. And finally, in repetition theory, basis elements, they are often very important because they are not just the basis, but they have some hidden structure. Usually, for example, if you look at the Kazhdan Lusztig basis, these basis elements, they are actually the simple modules in some modular pattern. So there are more than basis here, and we hope that once you get a basis with good properties, maybe there's a hidden story behind that, or something more than that. Okay, so now we turn up to our this problem. So the natural question is that can we compare the from Lie theory and basis from surface and this common framework from class elements? Okay, so in 2014, Thurston, in one of his PNAS paper, introduced the band basis, which has been known as band, for the skein algebra. And he conjectured that, like we will see the band basis too. He conjectured that it is an analog of the dual basis, namely the Kazhdan Lusztig basis for quantum groups. I want to say that at least from my point of view, this conjecture is a very well conjecture at that moment because we don't really have any evidence that why this should hold. Just do some combinatorial conjecture and say, this is an analog different basis without making any mathematical statement. What do we mean by analog? What properties is that? There's at least one property that we can expect because different basis for quantum groups, when the Gaussian matrix is symmetric, they are positive. Namely, if you multiply two basis elements and you decompose them, then you have a positive structure constant. Then we hope that if it is an analog, we conjecture that the structure constant of this band basis should also be found. This is something natural. And as far as I know, there's not much progress in this direction, even for the endless type. And then Brad Mueller, he proved that if you take the skein algebra of a surface and have an unpunctured surface, then it is actually a quantum class algebra. Here we assume it's an unpunctured surface. And actually, for the moment, there are still some technical objection to extend this to the punctured. Okay, now we have these two conjectures. This conjecture of Thurston in mind, and the Mueller's theory link the quantum class algebra from surface with link the skein algebra with the class algebra. And as I said before, we have a by analog of the different basis, we have a candidate, namely the common triangle basis. So these bases, these are really Kazhdan Lusztig basis, and they provide the analog. Now, the main result I want to explain in this talk is that for unpunctured surface, in this case, the skein algebra is class algebra. Then I claim that the band basis is exactly the same as the common triangle basis. And because common triangle basis is an analog of the dual basis when we study Lie theory, so it makes sense to say that this is an analog of the dual basis. Therefore, the Thurston's conjecture is true. And moreover, we can verify the structure constants are non-negative.
Sorry, so what do you mean by non-linear structure, you're saying it's atomic, right?
Right, magnetic structure, yeah, well,
I mean, like, you're saying it's atomic, right?
this is,
Atom.
no, it's not atomic. Atomic means that it is a minimal possible basis that has this,
Okay.
and it's the theta basis or the bracket basis that has this.
I mean,
This is not a minimal one with a positive structure.
yeah, I thought the Thurston conjecture was actually from Bojan about.
Yeah, but I think you can just about positivity.
That's
But atomicity actually fails.
I see.
So there could be many bases which are analogous to this.
Yeah, it's a very interesting phenomenon, but one we don't fully understand. So the surface provides a very good model where we can understand many things. So for skein algebras, now we know there are two positive bases. One is this band basis, which I claim here, and one is the theta basis, or the in the sense of gross heading Q on switch, or the which I proved with Travis Mundell that they are the bracket basis. So these two different bases are constructed using different Chebyshev polynomials, and they are different. So, and for band basis, because these are analog of the conjecture basis, you can imagine they are simple object, it's a monoidal pattern. And the theta basis is even smaller, so the other basis. So in skein algebra, there are the topological construction of some positive objects, which is even smaller than simple objects, which we don't fully understand why you have. Okay. Let me give you an example of class algebras. So we start from a least theoretic construction that brought 2,5 to denote a two-dimensional subspace or five-dimensional vector space, and A is homogeneous coordinate ring or equivalent coordinate ring of the affine point. And we have the Fluker coordinate Pij, and we have the Fluker relations. And for example, we can represent this one by two row vectors and two P24, the blue coordinate is column 2, column 4, the red part you take the minor. P35 is the blue columns, you take the minor, and then you can, this is the basic as linear algebra that can verify these two relations. So these are least theoretic construction of a class. And then this model also have a topological construction, you take the 5 form. So this is a disk with the 5 vertices on the boundary, and skein algebra has generators Pij. So these are the arcs connecting the vertices. And this multiplication is given by taking the union. And the skein, so here I work with the classical version. So I don't say which is above and which is below. And the skein relation is simply Pik, Pjl. It's something written like this. You can recognize that this is the same as the Fluker relation I have seen before. And for this 5 point, there are the very naive basis. You take the monomials of non-crossing arcs in this surface, and this give you a basis. Because whenever they cross, you can impose them. And this is to give you an intuition what is a class monomial. So basically, class monomial in a surface model, this is just you take any collection of non-crossing arcs and you take their union. This give you a class. Okay, so now let me formally define the skein algebra. So let's add sigma to denote the marked surface. Well, S is a compact oriented surface, and it might have boundary. And M is a marked points. Is a finite set of marked points on the boundary. So I assume all the marked points on the boundary. So this is called an unpunctured case. And by a curve, we mean a curve which ends at marked points and these vertices, or a closed loop without any ending. And if you want to obtain class algebras, we need to assume that this surface is triangulation formed by the arcs. And this is a mild condition. Most surfaces have this process. But there are exclusions. For example, you take the sphere with one mark point, not working out, rather than exclusions. And by link, we mean a multi-curve. By multi-curve, we mean a union of curves together such that they have transverse intersection. And at the quantum level, we endow this intersection point with an over and under order at this point. So whenever two strands of this multi-curve they intersect, we say which is above and which is below. And I use C is union of Wj Cj to denote this multi-curve where Wj means that there are Wj many component isotopic to this Cj. And because we are working with topology, we always using the work with isotopic classes. And now we take the base ring. In the classical case, the base ring we can take it to be the integers. And then in the counting case, you just insert a counting parameter Q half. And by non-negative or say positive elements, I mean the coefficient should be the natural numbers or natural numbers with Q plus minus. And skein algebra is simply the ring module generated by all the isotopy class of links modulo the following relation. So when you take the multiplications of two links, you just stack one link over the other. So this is non-commutative multiplications when there are the Q numbers. And the skein relation tells us that you have to take the equivalence of these things. So whenever there is a cross in a link, you have to resolve it left and right and up and down and insert some Q numbers. This is well defined. If you rotate the picture, you see it. There's no confusion in this definition. And so this is called the resolution of crossing. I want to say that the first one is the positive resolution, and I call the second one the negative resolution. And it is also important to say that we have a contractual loop evaluation. Whenever there is an unknot, so this is the closed loop which is homotopic to a point. And we say that it is equals minus Q squared plus Q inverse Q. And also if there is an R which is contractual to a boundary point, it is 0. And we have normalization at the boundary intersection point. So on the boundary, two strands, they are not at the same simultaneous height. You can realign them to pretend that they are not, it is not one above the other. It is they are at the same simultaneous height. And so insert some units and for normalization. Okay. So let us talk about the basis. A magic curve is called simple if it is crossless, so it does not have interior crossings. And its components are non-contractile, so it does not have arcs that's contractile point or non-loop. In this case, we call it a bangle. I don't know who first invented this name, but the bangle something decoration on your wrist. And we will endow it with ordering data because it has no interior crossing. So you only have to tell us about ordering of the strands intersect at the boundary. And at the boundary, it's natural to choose the simultaneous height. Right? No one is above the other. So this is our choice of the ordering. So this is the link now. Now we see that the bangle is the k-basis of this skein algebra. It is very natural because whenever you have a link, you have crossings, then you can resolve the crossing to decompose it into something which has no crossing at all. So that gives you a sum of bangles. And of course, it is something to do that you have to show that the bangles they are linearly independent. So it is very natural very intuitive from the definition relation because in the skein relation, you can no longer further reduce the bangles. But to prove it, I think one have to write down a few lines in Muller's paper. A basic example, we take this cylinder. So locally, so this is the local piece of the surface. You have a cylinder, and now you take 5 isotopic copies of a loop. And this is a bangle. And because union is a product, so it equals to L to the power 5 in the skein algebra. This is the basic typical bangle. And the bangle, you can imagine all the basics of the bangles. Oh. Now we want to twist this bangle a little bit. Let us introduce the Chebyshev polynomial of the second type, W. So U0 is 1, U1 is Z, and in a variable Z. And then we have this recursion Z UW equals UW plus 1 plus UW minus 1. And now you arrive at the recursive calculation of this, or equivalently, UW has this property. If you put Z plus Z minus 1, and this gives ZW plus ZW minus 2, blah, blah, until Z minus 10. So this is the Chebyshev. It looks a little bit like a SL2 representation trace, but I never truly know if there's a precise link to link this with the SL2 representation. And maybe topological people know this. Okay. Now let us be given any bangle C. So it is a union of arcs which I denote by blue, and the union of loops which I denote by red. And the bangle element is simply you take the corresponding isotopic class. And remember that you have Wj minus loop Lj. So this is Lj of Wj, a monomial in the loops. Now the band element is simply you replace this monomial in the loops by the Chebyshev polynomials in the loops. This was proposed by Thurston. And then because the transition from monomial to the same degree polynomial is an invertible transition, it is immediate to see that the band also form a basis. Yeah. Well, let us look at an example. We look at the classical case where the constant parameter is 1. And then Thurston showed that the band, which we defined it that using the Chebyshev polynomial on the loops, is a formal average of multiple. For example, look at this example, we have 5 copies of loops. And so you view this as the trivial computation of 5 elements. And then you can change it. So for any computation, you can change the front part of this cylinder into some diagram. So this is a very easy diagram in the computation group. This is not a great calculation, just use a computation diagram. And now for each computation, you can draw a similar picture. And now why not take the formal average? This is what you do with the finite groups. And you take the formal average of all the curves. This is coincide with the band elements. I think this is something related to a John Weisel projector in Temple aspects. Okay, now let us look at the class algebras and their basis. We still use a topological model to explain them. As I said, class algebra is an algebra which has lots of charts. Let me explain that in more detail. By a chart, we choose a triangulation. So triangulation is a collection of non-isotropic, non-crossing arcs of the surface and include the boundary arcs. And now we form a torus algebra. This is just a long polynomial ring of these arcs in this triangulation. And it has non-commutative product. We have just seen that before, so it's one put above the other. And on the normalization, so you have some Q number on the boundary normalization. And it has a binding evolution sending Q to the power D to Q power minus D. And now it's straightforward to verify that skein algebra is actually a sub-algebra of this torus algebra. Or equivalently, it means that every algebra element has a Laurent extension with respect to this local coordinate x1 to xn. And this arcs of the triangulation. And now we want to make sense of the highest Laurent degree, but this is not immediate because a Laurent degree is an n-dimensional vector. You cannot say which vector is larger than the other vector. So we should use a partial order on all the Laurent degrees. So this is called dominance order in the first paper, and actually here in the early work hidden in some proofs of early class algebra paper. So the name dominance order is actually imported from representation theory of quantum affine, and I first saw it from ICMS-Sofia. So you basically mean that if you have a highest weight module in the quantum affine, then the highest weight dominates other weights. And in particular, for any bundle, if you write its Laurent extensions in this chart, in this Laurent degree, it takes this form. It has x to the power g, the leading Laurent monomial, and with the sum of lower degree Laurent monomial, and all the g prime appearing there, they have fewer degrees than the leading degree g. And also, it is a well-known result in topology, I think, is that this bundle, so we call that bundle is a simple multiple which has no crossing and no contractual components. This bundle is uniquely determined by this leading degree. So there's no confusion to it. And some interpretation why we're interested in this type of form. So first, we twist this bundle, twist this loop part by using the Chebyshev polynomial. We obtain a band for that band. And the band also takes this form, xg plus something. Just the coefficient will change. And point g pointed. So this kind of Laurent polynomial is actually important because it reminds us of the characters of a highest weight module in representation theory. So x of g leading degree is like the highest weight, and then you have a lower degrees. And actually, this is one of the key points that is proposed, or at least hidden in the monomial calculation proposal of class algebras in Kazhdan and Lusztig paper. They really say that for some Laurent extension, they really can be realized as the characters, two characters of some simple modules. And G is the highest weight, and this coefficient in this type, then they should correspond to the dimension of a weight space in this module. And also in topological picture, this G has a meaning. So minus G in this picture, this is the so-called shear coordinates of the laminate associated with this family. So this is known to be to Thurston, to those Thurston, some important theory. So, and yeah, for people know pupil representation. So what is G? G is what you for us then. So it's approximation by classification object and G comes the multiplicity. Well, effectively, this is the multiplicity of a projective resolution. So in different areas, we arrive at different coordinates for this object. So we have height weight for modules, we have shear coordinate for the verticals, and we have a projective resolution dimensions for the objects in various categories.
Just to be clear,
Yeah.
if you were talking about the angle basis, you wouldn't say the same thing.
The Bangor basis, yeah, Bangor basis still take this form. So it's just the coefficient are different. Bangor basis also has this. So we first start with a Bangor is a simple multi-curve. Is a cross this
Can
multi-curve.
you go back into what's the difference in the form?
Yes. I should use a different node. So this is alpha. I should use alpha prime there. So coefficient will be changed.
Yeah, so it has the same form, or does it?
Yeah, it is it took the same form. It has a leading degree with low degrees.
So you wouldn't say the same sentences for that basis? Or would you?
Yes, I mean, if you don't know bangles and band, they have different properties. You would say the same, but yeah, in practice, so maybe I would say this like this. In practice, the band they are closer. Finally, it turns out that band they are related to simple modules in model located, not the bangles. Bangles are too naive.
So these remarks are with hindsight. They're not.
Yeah, this remark is just it give you a hint, but not every object of this form is a simple module. It give you some hint. It might be a good candidate, but then you have to make sure it is really the case. Okay, let us remember the Kazhdan type basis. So I give you a quick review. So let E be a free module over some RQ plus minus. Okay, it's a line vector space. So assume that you are dealing with some initial basis whose elements are sorted by some bounded partial order. And then there is a finite algorithm. By modifying this basis, you can obtain some good new basis, which we call Kazhdan type basis, or canonical basis for quantum groups or Beck algebras, whose elements now become invariant under the bar motion, sending to inverse. So because the initial basis may not have this process, so we'll modify. In some sense, this algorithm shares the spirit of Graham-Schmidt process. So we start with a bad basis, and now you correct it term by term, you get some orthonormal basis. This is similar. So you correct term by term, correct any basis element by low terms to obtain some binary values. And the importance of such basis is that if you an algebra in practice, an algebra with a Kazhdan type basis is often categorized by a monoidal category and has a product such that the basis element corresponds to the simple modules in this monoidal category. This is why they turned out to be very strong. Okay, now in one of my first paper, I introduced the so-called common basis for many quantum class algebras. I will first give you some remarks. So first, it is the only known Kazhdan type basis for quantum class algebras. So from this point of view, we expect that the basis element should correspond to some objects in an appropriate monoidal category, like other Kazhdan type basis. This is our hope. And I also comment that this basis, when I define that, it is defined to encode all the desired properties. So I encode several conjectures into the definition. The cause is that I don't know if it exists or not. So existence is a difficult problem. The uniqueness is automatically follows from the definition, and the good property follows from the definition by existence. And then I show that if you take the quantum unipotent subgroup, the Kazhdan type, UQ and W, and this is a quantum class algebra. This is known by the work of Geisler, Schwann, and Yakimov. And then we show that in this case, the Duquesne basis is exactly the same as this common basis. So from this point of view, this definition of the triangle basis includes the Duquesne basis. So this is a Duquesne basis here. And the more recent work, I show that for almost all class algebras from Lie theory, they actually possess this common triangle basis. So that's something drawn. And moreover, when the Gaussian matrix is symmetric, the basis elements they actually correspond to simple module in some monoidal type. This is not exact monoidal calculation. You have to change the Q center of the algebra a little bit to make the correspondence precise. But basically, this monoidal calculation it captures all the information of this. Okay, so What I want to say is that for the moment, in the least theoretical part, the class algebra and their bases are well understood, and we really have an analog of the different bases. And now we ask, can we do it for other type of class algebra, which do not come from least theory? For example, the skein algebra. So actually, the big hope for me is that we can do it for higher particular theories class algebra. For the moment, we can only do the skein algebra. So these are the SL2 local systems. The SL2 is always the easy case. So let us consider the basis. First, we need to have an initial basis for class algebra. In a topological picture, we can construct it like this. Let there be given any variable like this C. This is a curve, so this is a angle. And we can slide the endpoints of this arc by one of these, the extended endpoints of this interior arc, so this red one interior, by one interval clockwise. Well, clockwise or counterclockwise, this depends on information. So I will obtain this blue one, C shift by one. This can be applied to any arcs. And some explanation. This actually is a shift function, corresponding to the shift function or the orthogonal translation in the corresponding class category. So this is why I denote by shift one. So this is a suspension function in the translated class. And for this class algebra, it is so-called Donaldson-Thomas transformation. So basically, this is a green to red sequence, if you know the class algebra. Special sequence in the sense of, well, this name comes from the constable transform as non-primitive Donaldson-Thomas invariance. So basically, you take the joint action of the motif of the part of some perfect derived pattern. This gives you a Donaldson function. And if there's a monoidal category, if you are familiar with that, this one is the right dual in the monoidal category. For example, it's a quantum field. Okay. So now we have this shift to the one operation. Now let us draw the initial basis. We can draw an ordered product IG. So you take this form, you Q to some power, and the product of Xi from some initial triangulation. So these are non-crossing. And now you shift, you slide every R in the initial triangulation to shift by one. Slide every interior R then shift by one. So let me explain. G is the leading degree. So this product, everyone has the highest degree. So G is the sum of all the highest degree. And we want it to be reduced. So one of xk or shift of xk, only one of them can appear. And this Q beta is just some normalization coefficient. So that this leading degree has coefficient of 1. Otherwise, it will have degree Q to the power of minus beta. And some explanation of this strange definition. So the bundle, if you are given a bundle with highest degree G, so bundle is a certain. Remember that the Laurent polynomial it has a leading degree G. And this bundle is actually categorized by trivial representations. And these trivial representations will have an injective resolution by the injective module. So D and D prime is actually matrices of the injective resolution. So there's a representation theory explanation of this leading degree and D here. And why we choose it to be reduced? Because we want minimal resolution. We don't want a cyclic complex IK to IK. This is actually redundant. So this is the ordered product. So why is it formulated like this? Because you want an analog of the PW basis. Remember that. So we have PW basis to apply the Kazhdan algorithm to get a bi-invariant basis. And PW basis is an ordered product of some good elements in the quantum group. Now we take good elements in the class algorithm. So these are R, these are slide of R, and we take the ordered product. Okay, the first thing we can observe is that this collection is linearly independent because they have different leading degrees. This is automatic, and they are naturally sorted by their highest degree. This is also automatic, and it is actually a topological basis. Namely, for any Laurent polynomial effect, it can be represented as a convergent infinite sum of these different Laurent polynomial with different degrees. This is also a very easy observation. But unfortunately, the first difficulty is that this is not a basis in general, and unless the class algorithm is acyclic. This is not a basis. This is just some independent set inside the class. Now, nevertheless, let us pretend it is a basis and we apply the Kazhdan algorithm. Well, these are linear independent sets, not basis. We apply this algorithm, and we will get formal Laurent series. So why? Because this algorithm will never stop because our partial order here it is unbounded. So not unlike the partial order of a blue hat order, it is bounded. So after several steps, it will stop. here it is unbounded order. So we will get infinite sum of these initial elements here. So you will get some a priori you get formal series which become bi-invariant, and the formal series that you have leading term H and corrected by lower terms. And we require that the coefficient of the angle coefficient lies in the negative power of Q's, and this will give you a unique solution. This is standard and routine algorithm. You never stop, you get some formal series.
So sorry, how do you get the Lorentz series on it?
Yeah, so it's like you imagine this is the basis or whatever. So you start with H of order product. This is not bi-invariant. Now we can correct it by lower terms. By low degree terms. So we first make sure that you only have the leading term bi-invariant, that because coefficient 1, that's bi-invariant. Now we cut the other terms by the lower degree guys. And we cut, we correct it many times.
We just do this process.
Yeah, do this again and again, you get some bi-invariants. In Nagjima's paper, I think he wrote this explicitly in a lemon. And in earlier work of Lusztig, there is also some available. Okay, so now this is the point where we put all the conjectural properties inside it. If the skein algebra, we assume the skein algebra has a basis, or more generally, we assume the class algebra has a basis, such that this basis for every chart. So remember that this order product depends on the chart or the triangulation you choose. For every chart you choose, it coincides with unique solution of Lorentz series. Then it is called the common triangle basis. So this we encode several difficulties here. First, we don't know for any chart, we don't know if this process gives you really Lorentz polynomials. This is unknown. And even if it gives you a Lorentz polynomials, we don't know if it form a basis. The second unknown things. And the third thing that for different triangulations, we select for different pizza basis. We have many different solutions. We don't know if they are really the same solution. So third difficulties. And we assume all this happens and all these are formative, we get basic called function. So we encode all the difficulties in this definition. And in practice, like we want to start with something which is really, really good, like number basis, and verify all the properties are actually. Okay. I want to say that this basis is actually determined by the following conditions. So first, it includes all the class monomials. Remember that these are 97 union of arcs. And moreover, it has some triangularity. Namely, if you take any class monomial, this is union of arcs, and you multiply it with the basis element, you have this triangular decomposition. So highest term LH is the lower terms. I want to say that in monoidal category, so after the work of Thurston, Lusztig, and later Kazhdan, Kim, and O, I think we understand this better in monoidal category. This property means that in monoidal category, we multiply the class monomial with a simple module. And now the tensor product is usually not a simple module, but it has a simple circle or simple head according to the convention. So this leading term is actually a simple circle or simple head. And these other terms, they are the other part. It has some, and this Q degree tells you that different composition factors, they have a well arranged Q degree distribution, which you can control. Okay.
Here, we need to consider forward variance for something.
For every C. Yeah. So in the circuit table, we need to compute all the transitions.
We need to take the function for all.
Yes. It's like you need to compute all the pizza bases. Okay, so the first result is that for unpunctured cases, the common triangle basis, what I mentioned in the overview. So in particular, it is the Thurston conjecture that this the Newton basis is actually verified. And what I think is funny that after this result, that this because the common triangle basis is certain Kazhdan Lusztig basis. So this means that we actually have a topological picture for Kazhdan Lusztig basis. I mean, in the Kaiser limit, it's a formal average of all these arcs, all these curves. This is something we can draw a picture. Now you see that. So Kazhdan Lusztig basis, they are not just curve shapes. They are formal average of this computation root. At least in SL2, we hope, I mean, in G-level system, I don't know. So this gives you some hint. If you are very clever, you know how to generalize this picture to the web basis case, maybe you have a good candidate. What is the version of this Kazhdan Lusztig basis for the high maximum? Okay. Some comments. Recall that the commutative basis has a multi-type basis, and we would categorize it from D theory. I say that for many D theory, we have simple modules. We hope similar result to hope for the staying algebra. Then you have a basis, we hope the basis elements are actually simple modules. And for the moment, we know that in skein, for topological side, we have TQFT or many constructions, but after I check the literature, at least there's no available monoid category at the moment that make this statement precise. Hopefully in the future we have good monoid category. But in particular, the band basis shouldn't have non-negative structure constant because these are simple modules. And the structure constant are the tensor multiplicities that you have tensor product. And the second result is a paper I'm writing, so I will not explain much. So when the surface is unpunctured, these structure constants are really non-negative. I want to comment that actually Kovalik from topological side actually can verify this positivity of the band basis in another direction. It verifies for closed surface without any mark points. When the closed surface is not a torus, this is positive. This is a purely topological result and use a lot of Covenant homology and calculation. So it is in a very different direction than class algebra. So if you are working with topology, closed surface without any mark point is a good situation. That is compact without anything bad. For working with class algebra, we want lots of mark points, and we want this unpunctured case. This is the best case in class algebra, but the worst case for the topological case. We're in different side. Yeah. So finally, let me explain our approach to result one and how we verify this triangle basis. I think the phenomenon is quite funny. So remember that we want to compute the class monomial multiply a basis element. So here we want to compute the product of a class monomial with a band basis. So here I use a green part, this is Z. So this is a non-intersecting union of arcs. Here I will draw one arc. And the blue part is a degree G manifold here. So it is a union of two arcs in this example. Now let us compute the product. Let's say this triangularity imposition of the product is crucial. So when you take the product of green part with the blue part, right, it has crossings. So you have to resolve it. You resolve it into many multi-curves. EI is you have a positive resolution or negative resolution everywhere. You resolve it in sum, and Q to the power beta I depends on you resolve it positive or negative. So this gives you different coefficient. And inside these multi-curves, you might have contractile part, the non-loops, the unknots, which we don't like. So inside this multi-curve here, we have the red part. This is the unknot. Here, for example, in the picture here, we have two unknots here. And in the last picture, we don't have any unknots at all. We have two isotopic loops. So anyway, you have some unknot to be included in your resolution. And each unknot is a constant, minus Q squared, minus 2, the constant. And to the power of Ni is the number of unknown Q. Okay. And we have a very specific resolution. If you resolve everything positive, you get this part, this gray blue part. So this is multiple obtained by all the positive resolution, and you will get some isotopic copies of essential groups of groups which are not controlled. So now let us imagine that the triangular basis exists. For the moment, we don't even know the triangular basis exists. Imagine the basis exists, then we have this triangularity imposition. So that multiplied with the degree G triangular basis should have a leading term with lower terms, and lower terms have fewer Q degrees. And if what we want is true, if the band basis, this is the Chebyshev defined basis, and is really the triangular basis, then we can compare the leading degree terms in the deposition, and we can show that in this case, if this is true, then the leading degree term LH is actually given by the sum of the multi-curves in the multiplication of Z with the band with the highest affinity. So basically, the band and the band they are not the same, but they are not so different. They are only different in our terms. When you only look at the highest degree term, they should be the same. This is what I want to say. So assume everything is good. Okay, now let us analyze. So the problem is now because you want to understand the multi-curve which has the highest Q degree, how can we write it like this? You want them to sum up to the band basis, sum up to the Chebyshev monomial factors. So let us compute the highest Q degree. So what is the Q degree? Q degree is Q to the power of beta I, so this is obtained by the resolution. And also Q to the power of 2ni, this is obtained by counting the unknots appear in the resolution. You sum them all, so this gives you a Q degree. Now let beta be the leading one, and we let E12 to denote all the magic curves which contribute to the leading Q degrees. So here we have many magic curves which are obtained by resolution, but E12, those in E12, they contribute to the highest Q. Then the crucial statement is that we want to show this positive resolution is one. You take the band basis element, and it is actually the sum of all the top Q degree magic curves. And you see that here you have Q2ni, so this will give you a minus sign, so minus 1 to the power of ni. So it is the alternating sum of all these highest Q degree. I mean, the calculation might be a bit complicated, but what I also say that it is only important to understand the highest Q degree term. And highest Q degree term of the band basis, so this is some Chebyshev polynomial definitions. It should be, we want it to be coincide with the magic curves which contribute to the highest degrees. So this is something you want to understand. Now let us understand all these magic curves which contribute to highest Q degrees. We discover the following. So there exists non-intersecting annulus embedded in this surface. Such that for this important magic curve which contribute to the highest Q degrees, they are not randomly distributed around this surface. They are actually contained in this annular region. Actually, they are safely arranged in this annular region like the beads on a necklace. So the annular region is a necklace and they are like this. For example, we have in our first example, we have these three magic curves which contribute to the Q degrees, and you have these two unknots and this one unknot and one unknot. And moreover, these different magic curves contribute to the highest Q degrees. They are unknots. They only differ at the unknots. And unknots, they are connected by merging and splitting. Here you see that you can merge any two unknots and you get this one. Or you can merge in another way. And if you merge them all, you are not left with unknots, but you are left with these two isotopic copies. So this is an alternative resolution. So all these, you see that in this example, all these four magic curves, they contribute to the highest degree. And the three of them have unknots, but unknots can really combine and merge or split. And if you merge them all, you get something without unknot, but this is exactly your leading unknot, so this is something with isotopic. And now you sum up them all, then we claim that this is the sum all these things together, this give you the band basis, namely is a twist of these things that Chebyshev polynomial. So in this example, that this bamboo is the black part, R part, with these two isotopic copy 2 power of L. And you take the band basis, so you twist this 2L by the second Chebyshev polynomial is L. So this is actually coincide with L squared. So this one plus 2 copies of -1, because here you have two unknots, each have one unknot, plus 1 copy of -1 squared, because here you have two unknots. So you calculate them together, this coincide.
So the 2L part is the band one, actually a band.
So which
2L part. So it's not really a copy of 2Ls, right?
Yeah, this band part is not.
Yeah, it does band part. Okay.
And one last minute, maybe a few comments. So unknown, the situation of unknown. So previously unknowns, they appear in the calculation of scales. They are very annoying because they appear in your calculation, but they leave the Q degrees of multiple. They make it difficult to understand where is the Q degree. And they are not essential because eventually they will become constant. So usually we will try to get them out, get rid of them as soon as possible. But now unknowns, they are important. They form a beads on a necklace. They have very interesting combinatorics like merge and split. And this combinatoric fixture is exactly why we get Chebyshev polynomials. So the natural question is how we interpret this object in representation theory or calculus. We don't know for the moment, but we have some past experience. So firstly, in acidic, if you look at the derived calculus, or you look at acidic complex, right? So complex with trivial homology, they will be evaluated as 0 in derived calculus. You will get rid of them. But they are essential because this simply use this information can be used to realize the garden part of context envelope as well. Where while, so this is in the work of Kazhdan, or you can construct corresponding pro shapes over cryptographics. This was in the real world of myself. So this means that this use of this information is actually important in some extent. And here, this use of this unknown, they're really important to get checked. Okay, so this is what we have explained today. We have class algebras, polynomials, and skein algebras. But we have some unknowns and necklace phenomena which we do not understand. Thank you for watching.
I just have some quick questions about this. So when you're talking about this unpunctured surface,
Yeah.
is there any additional condition we should have? Let's say something like, I guess, the paper actually discussed that the number of points on the boundary should be less than, like more than, let's say, one or something, those kind of boundary conditions. Do you also have that?
Yeah, for having class algebra, we need a translation. So
Yeah,
we
yeah.
need that every boundary component has at least one math point. One math point. Yeah, and I think that's enough.
So each of these, okay.
Yeah. So in Muller's paper, I think he assumed that there are at least two math.
Yes, yes.
But I think this is not important. Yeah, actually. One math point.
The expectations about punctured case.
Yeah, the problem is that here you see all the arguments they rely on the resolution of crosses, right? So essentially that you want to understand the algebra and then we multiply two algebra elements by this resolution, you can calculate this product locally. That is crucial. So it makes sense of talk about angular regions and local operations. But in a punctured case, we have a globally defined quantum class algebra. But the fact that no, we don't have yet a way to calculate the product of two algebra elements as locally using resolutions. That's something missing. The main difficulty is about at the puncture you have tagging and untagging. In the classical case, we have some way to resolve it, and we don't have quantum handle.
Something there.